All right. So this isn't going to get y'all in trouble yet. Um, how many of y'all actually went through like, your unit twos and threes to try to understand what the chapters are saying? Like read them. All right. So make sure to look through chapter two. That stuff is coming up due. I gave y'all a little extra time on it. But like it's very important to try to get the book stuff done. uh I'm not saying that it's going to make it, like, the book stuff isn't necessarily easy, but if they can say it a certain way and then I come back and explain it, I think that's going to help you learn rather than it being the first time you ever experience it as you come in. Okay. So I'm going to Boolean algebra is coming up next, and I'm going to put that due Sunday night, 11:59. I'm asking you to look at 4.1, 4.2, 4.4, and 4.5 and do the questions on those. Now, the thing is, those have answers. So, am I necessarily looking for you having the right answer? No. What I'm doing is I'm giving you stuff that has the answer so you can check yourself and make sure that you're on the right track. I mean, if you do it, you're going to get 100, but if you do it and get 100 and you still don't know what you're talking about to at least a little bit, then it didn't help. It just became busy work. And so, the most important part of all of this is trying to get it so that you're doing it for understanding. Okay. Let me see if I can get this any bigger. A little bit bigger, but not much. See if I can get this. We're just going to have to deal with that. All right. So we're going to look at Boolean algebra a little bit. Now, you got a lot of rules in Boolean algebra. All Boolean algebra is dealing with trues and falses. Okay. All right. Is it on or if it's off? You're going to have rules like this. A and 0 equals 0. Okay. And what that's doing is we use a dot for an and. Okay. Because we don't necessarily want to draw out this every time. Like, and if we're typing it out, it's impossible. Okay. And we use a plus symbol for or. Okay. And if you draw out the circuit when you're doing this Boolean algebra, it's going to make sense. Okay. Because when is an AND gate true? When all of the inputs are true, right? So if we have a 0, oops, we're getting a 0 out of the AND gate, aren't we? So if we AND anything with 0, no matter how complicated it is, if you see an AND with a 0 on it, it's always going to be 0. It doesn't matter what preceded it or beside it or whatever. That part is going to be 0. Now, A and 1 gets a little bit more complicated. That's going to be A. Okay. So that A is representing a variable. All right. So we've got 1 right here. And whatever we put in this side, like, so we're saying A is our variable. If we put a 0 in, a 0 on an AND gate is always going to be 0, right? If we put a 1 in, we're going to get a 1 out because we got 1 on both, right? So A is our variable. We don't know what it is. If we have a variable we don't know what it is and we've got it ANDed with a 0, it's always going to be 0. It doesn't matter what the A is, right? If we AND it with a 1, we need more information. If the A is a 0, getting a 0 out. If the A is a 1, we're getting a 1 out, okay? A or 0 is equal to A. Okay, so we've got an OR gate, and if any of these is equal to 1, we're going to get a 1 out. Well, if one of them, if we've got a 0 on an OR gate, we need more information. If that A is a 0, the output's going to be a 0. If the A is a 1, we've got a 1 on input of a 0, we get a 1 out. So a variable ORed with A is going to be equal to whatever the A is. Okay? A or 1 always equals 1. All right, because we've got that 1 input that's already high, and that's going to drive it up there no matter what happens. Okay? Now, I think it's got 12 of them in the little list of Boolean expressions, you know. You're going to memorize them because they're all going to make sense. Okay, after a little bit. It took me a while to get it down to how simple it is, but you're going to have like A and a not. We put a line over something to show not, right? If we AND anything with a 0, we're going to get a 0. A ANDed with and a not is 0, always. Because if A was a 1, A not would be a 0. If A was a 0, we already got a 0 to make that AND gate a 0. Okay? Cool? A ORed with A not is always going to be a 1. Because if A was a 0, would have a 1 as a not, we got our 1. Right? If A was a 1, we already got a 1 to make the OR a 1. All right, so that knocked out 6 of them, right? A double not is equal to A. So if we invert A, we get A not. If we invert A not, we get back to the A. So if we double invert something, we get right back to where it was. It's a double negative, okay? Like if A was a 0, it'd be 1 right here. 1 going into that would be a 0. All right. Now, the other sets are a little bit more complicated, but what I want you to do is give a good college try at reasoning those out because they are able to be broken down to something like this, okay? Because we're going to hit that and we're going to hit it hard, but I don't want to hit it so that it takes forever, okay? I want you to give a good college try at all of those that are on that little rule table, which is first part of Unit 4, okay? Something else I want you to get good at. Y'all looked at truth tables yet? All right, a truth table gives us a bird's eye view of how a logic circuit works, okay? So if I had a 2-input circuit, how does it work? Now we're going to do an AND right here because we know how an AND behaves. So we'll say a 2-input AND gate, all right? if we've got two inputs, that means we've got, let's just put random variables there, A, B, and traditionally we'll probably do like a Y for an output, okay? How many combinations of two things do we have if they can be on and off? It's 4. All right, so it's going to be 2 to the 2, okay? All right, so we've got where both of them are off, where the second one's on, where the first one's on, where both of them's on, okay? So this is why counting in binary is pretty important, because if we have 3 inputs, we'd have to double that, right? Because it'd be 2 to the 3. 2 times 2 is 4, times 2 is 8. All right, so a 2-input AND gate is only true when all of the inputs are true, right? So this is the only place that is going to be on. Every other time it's going to be off. All right. Now, truth tables are extremely important, okay? Like, when I look at a truth table, like, you know, I can get a lot of information out of that without, like, tracing things with my brain. Yeah. Do what? Yeah, so, yeah, so, like, if I've got a 0 over here on an AND gate, I've got a 0 out. The only time that I get a 1 out of an AND gate is if all of those are true, okay? Now, a 3-input AND gate, we've got 3 inputs, so we've got 8 different things. The only time an AND gate is true is if all of the inputs are true. And so the only one out of this that is true is this one, right? So we'll have A, B, C, and then Y. Okay. Let's do an OR gate. 2-input OR gate. We've got 0, 0, 0, 1, 1, 0, and 1, 1. Anytime you've got a 1 on any of those inputs, it's true. So the only time it's false is if everything's off. All right, let's do a 3-digit or 3-input. All right, the only time this is false is if all the inputs are false. So 3-input OR gate looks like that. Okay. I need you to get in your head to be able to look at this and understand its function. Okay. Because we might have a complicated function that like has a whole bunch of outputs, and well, let me show you one. Okay. Without drawing the circuit, so we got 0, 0, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0, 0. Let's make something useful now. I told you you could make anything out of ands, ors, and nots, right? So we've got these inputs. And then let's say that we've got We've got all those outputs. Actually, we don't need that, the eighth output. All right. Now let's say that we had all these little LEDs, and above this LED, we said 0. Above this LED, we said 1. Above this LED, we said 2. Above this LED, we said 3. And we're going to make a binary to decimal converter, right? So that if you put in a binary number, if you put in 111, it should output the LED that, like, let's say the LED is behind a little number that's like clear that says 7. So it shows 7. Okay? All right. So the way this would work, boom, 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 right? Y'all cool? Like the only time that 0 LED is on is if they're all off. Okay? Only time that 1 LED is on is if we're at 1 in binary. Okay? So now, if we count up in binary, those LEDs would just go 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. Okay? So this is a legitimate truth table. Now, I'd fill in the rest with zeros, but you can understand that the rest are going to be zeros.
You make something like that with once 2 turned on, with 1 cut off.
Mm-hmm. All right, because like you're looking at it as exclusive. Like whenever we're in binary 2, we don't want any other light to be on. Okay, so I'll show you how to build that real quick for a few numbers. Okay. All right, so for the 0 LED, right? When do I want it on? When everything's off. All right, so the way I could do that, an AND gate turns on when everything's on. I've got a 0, 0, 0. I need to convert into a 1, 1, 1, right? So I could put an inverter right there, and so when I take that 0, it'll become a 1. I put another inverter there, so if that other 0 becomes a 1, and then I put another inverter there, so that 0 becomes a 1, right? Cool?
Would you have to use the 3 input?
Mm-hmm. All right, so now I want the 1 to come on. All right, so we're going to say this is A, B, and C. All right, so C is already a 1. We don't need an inverter for that, do we? But we still need one for A and B. Are y'all starting to see the power of this? Like, yeah, so like with this way, like if it's a 0 and we want a 1, we'll put the inverter in, right? So with this, we can just use a 3 input AND gate over and over again. And if there's a 0 in there, like number 7, we don't need any inverters, do we? Like number 7 is just A, B, and C, and then that's going to go to the 7th one.
And then for the 3rd one, you would put a inverter, and then a regular one, and then an inverter.
Yep. So, like, I would look at number 5. I've got 101. No inverter, inverter, no inverter. Okay? Yeah, so, like, all these C's would be tied together, right? So, you know, somebody could be flipping switches, and then now, like, it's telling you what those switches are doing. It's a binary to decimal converter. Okay? Cool? Or a sequencer like what we did in PLCs. Like, we could have the computer counting up in binary, and then we could be sequencing things to happen one thing after another. Okay? I'm gonna give you a good one. Have y'all looked at the XOR yet? The exclusive OR. All right. So an OR gate, if any of the inputs are true, then we get a true. An exclusive OR only gives us a true if one or the other is. Now, we don't have anything but 2 input XORs, okay? But this is one of the most powerful components that we've got. It's got an exclusive OR, but we also call it, we use this for inequality. And it makes sense. We're saying if the 2 inputs are not true, or are not the same, it should turn on, okay? So if they're both 0, they're both equal. Those 2 are 1 and this one is 0, okay? But I also told you that like everything can be made out of ands, ors, and nots, all right? So what we're going to do is we're going to make an exclusive OR out of ands, ors, and nots, okay? All right, so we can take this truth table and we can make it so that it turns on with ands, ors, and nots based off of this, okay? Because an XOR is just a combination of things, but we've got a symbol for it because we use it so often, all right? All right, so the equation for it is A and B naught, or A naught and B is equal to Y. Okay? So when is it true? All right, so that one right there is A naught B. Okay? This one right here is A B naught. So if either one of those are true, the output's true. Okay? So we can make this out of an AND gate. So we've got an AND gate, and we're feeding A into it. And then for B, we're going into an inverter. And so we've got 1/2 of this. Okay? Or if it's all right, now as we get going, I can't draw over a wire, right? Like doing a little loop over that makes it more complicated. If it goes across the wire, like right here, but it does not have a dot on it, it is not connected, okay? So I'm going to take this right there. So A and B naught, this would turn on. A naught or and B, this would turn on. Okay? So that's how, and if either one of those are true, either or of those, that's an XOR right there. And we built it from ands, ors, and nots, right? Now, that's a pretty simple circuit, but do y'all see how that works? If A is 0 and B is 1, all right, 0 is right here. This one's not going to turn on, but that becomes a 1 right there because it goes to the inverter. And this one's already a 1. We get a 1 there, a 1 on the OR gate, we get a 1 out, right? So I just built that off that truth table. If I have a 0, 0, I've got a 0 on this AND gate. That's not true. There's a 0 over here going directly to this one, so it's not true, right? Because the B is a 0 right there.
But if you put an inverter in
Yeah, but what we're trying to do is make it work as an XOR, which means that, you know, it's an OR gate, but it's an exclusive OR gate. Like we're not counting the times that they're all on. Okay. Why is that powerful? OR gate's super powerful, but an XOR is powerful. Let's say that I have a circuit and I've got a bunch of numbers coming out, and sometimes I want those numbers to be the numbers that they are, right? And sometimes I want to flip those numbers. So if I put a 0 in, I want a 1 out. If I put a 1 in, I put a 0 out. So if I want this case right here, I need an inverter, right? But I've got a case. There's a bunch of cases where some numbers we want to invert and some numbers we don't, right? So what we can do, all right, so we'll call this input, output. Now let's do our little thing here to remember, okay? I put a little switch right here, okay? And I'm going from, I've got a 1 and a 0 here, okay? If I've got this on 1, if I've got that little switch on 1, and I put a 0 in over here, what do I get out? I get a 1, right? Because of these two numbers up here. Got a 1 and a 0, I get a 1 out. If I put a 0 or a 1 right here, I've got a 1 and a 1, I get a 0 out. So what is that doing? Like it is, all right, so a 0 and a 1 will give me a 1. So if I did a 0, a 1's coming out. If I did a 1, a 0's coming out. So when I put it over, I put the switch over on high, right? It becomes nothing more than an inverter, like a NOT gate, okay? Then, but if I put a hard-coded NOT gate there, I can't get a non-inverted number, can I? So if I put this down to 0, what happens? If I put a 0 here, a 0 and a 0 is a 0, right? So a 0 is coming out. If I put a 1 right here, a 1 and a 0 is a 1, so 1 comes out. So if I turn that off, it doesn't invert anymore, do I? So with an XOR gate, one of the things I can do is make a switchable inverter. So sometimes I want it so that the it doesn't invert that number, and sometimes I want it to. I use that inverter, and if I put one side to 1, then it's going to invert everything that's going through the other side. Okay? Cool? Let's do that. Y'all want? Let's do that. We're going to put it in deeds. It's on that second video. I only put up like maybe a 20-minute video for the lab part.
Is it on Canvas?
Yeah, it should be up by now.
I tried to find your stream.
Yeah. Well, like there were videos already up, and then I did a little piece of a video to show them and whoever else the type things that we're going to do in the lab. So, it is for AC. It'll be a physical one. Y'all are going to use that.
That's for AC more.
It is a pretty legit one. So when you get it, pull up deeds. For this class? Not really. Like, certain jobs you're going to have to take like a technician's test, but the vast majority of my people, they get like higher than 90, where most people are getting like 50s and 60s.
You gotta take one for good still.
Like we kill it consistently against any of those tests. Like my guy at Camtech, they told him that he could sit for an interview if he got over a 50 on the Ramses. He made a 96.
What's that test like?
real simple electrical, and then they'll have stuff that is mechanical, which I can tell you a couple of tricks for that. Like, let's say you have 5 gears, and like they say that, all right, this gear's got 10, this one's got 4, this one's got 8, this one's got 12, and people will be trying to figure out their ratio. Like, if this one was turning, how many times this turns. Thing is, like with the gear train, like all of those balance out. So if you have 10, 4, 5, 4, 4, 2, whatever, ignore everything in the middle and just look at the outer 2 gears. Like, so if the first one's 10 and the other one's like 20, you're going to have a 1 to 2 turn, right? Because it doesn't matter what's going on. Their ratios are going, and I'll show you later, but like a lot of people will spend 5 minutes trying to be like, okay, well, if I turn this one once and that one's going to turn 4 times and that one's going to turn 2, and they overthink it. But if they're all connected, those outer ratios are the only thing that matters on that part. One quick thing to do that people don't really think about is if you've got one gear and it's turning clockwise, then the last gear is turning clockwise too, right? If you have 2 gears, the first one's turning clockwise, the other one's turning the opposite of that. So if they're trying to tell you, like, what direction is this gear turning, count the number of gears. If it's odd, right? Like the 1, it's turning in the same direction as the first one. If it's even, it's turning in the opposite direction of the first one. Don't even care about anything else. If they're asking you what direction it goes in and the speed of it, just look at the outer 2 and then figure out how many are in there. Like if it's an odd number, just think back to 1 gear is turning in the same direction as itself, and that's an odd number. Yeah. Oh yeah.
I bet they use it last night. I sat there trying to figure it out. It's just
I will do that. It doesn't. Well, go down to uh, type here to search and start typing in deeds.
I like 5 YouTube videos after that thing trying to explain it, the trigonometry stuff.
Yeah, I'll help y'all. We'll get out a little bit early in here and. If the next one doesn't, like, try to download it and get it on there, because I want them on all the PCs.
The motor controls class one.
Is the motor controls class what? I like it. Like, mm-hmm. Yeah, it's pretty legit. Hmm. We're going to do a couple of things, but the first thing we're going to do is an XOR. All right. So there is a schematic symbol for an XOR. Like, I want to put this up and then like give y'all some time to put it in. Like, it's the 6th thing over, And you notice that like it only has two inputs. Like you can do an XOR tree and build it out, but we're only going to do a two input XOR. All right. And then on the bottom, we're going to put a switch. We're going to connect that switch to it. Now, instead of having to push a button and do all that good stuff, I'm going to show y'all something else we can use. On the inputs, go to clock generator. I just want to give you a 0, 1, 0, 1, 0, 1, 0, 1. Okay. So put that clock generator in there. And we'll see if that's slow enough to actually sit. And go ahead and connect that. I didn't really change it. I was just checking to see if it's something we want. And what we're going to do is we're going to put two LEDs on here. Okay. Instead of putting like something to show a 1 or a 0, go to test LED under outputs. And we're going to put one right, like if you right click it, you can rotate it. We're going to put one on the input and we're going to put one on the output.
Right click.
Oh, sorry. There's a right there. It's called a test LED. Like, so on the output, go to like near about the bottom. It's right before the bottom.
What's that thing on the very end?
It's a test LED also. And when you play it, like nothing, like it's going to say current file, modify, save it, say yes. We're going to call this XOR 1. Now, both of them are off. That's because we don't have the clock going. So go ahead and click that clock. And like every time you click it, it's going to change the state. Okay. If you right click it and do enable clock animation, it should start going back and forth for you. Okay. All right. Now, once you got that going back and forth, go and click the invert button. And now see that like it's going to be the opposite of whatever the input's going to do. Okay. In here,
Not on these, but like
we've got a couple of bigger things that we'll do. Because I simply don't have enough physical like ands, ors, and knots. Like when we make the microprocessor, you're talking about like 100 things, and the biggest chip that I've got has like 8 AND gates, right? So a lot of stuff we have to do in these, but there's a couple of things that we'll do on the breadboard to help you understand that like in the real world you can do this also, right? It just won't be to the extent that we could do in these, right? But we'll definitely link some LEDs and stuff. All right. All right. So once you see that that works the way you want it to, right? So if I don't invert it, it's following the input. If I do invert it, it's inverting the input. What I want us to do is I want us to build an XOR from scratch, because I let us get a little too ahead of ourselves. In this class, I don't like us using something like over here. We've got like decoders and encoders and multiplexers and demultiplexers and complementers and adders and all that. I don't want us to do any of this until we build one. All right, so I let y'all use an XOR before we built one, but we're not going to do that too often. All right, when we drew one up, what did we do? We took 2 AND gates, and we're going to prove that this works the exact same way because it's the exact same thing. We took 1 OR gate, we took 2 NOTs, and we're going to take that clock generator, and we're going to take input switch, and we're going to make the same thing happen out here, right? So we had B tied down to this little switch down here, right? So we go up to this inverter for that B, and we go straight into this one. That B, right? And then we tied A and off of this side of A, we want the non-inverted part. We're going to run over to here. So we've got B and B not tied to here, and A not and A tied to there. And then we'll just finish out the circuit by ORing everything together. And then what we're going to do is we're going to put a test LED right there. Test LED on the output. So through that truth table that we did earlier, we saw that this should be equal to that, right? And the logic inside of that symbol is this, okay? Like that's how they made that exclusive OR. So we'll play it, we'll go ahead and save it, and then start clicking on that clock animation, right? And if I flip this one, it's going back and forth. Clip this one, it's going back and forth, right? All right, so we just proved that we could make an XOR from scratch, right? All right, now you're just gonna have to trust me that having a programmable buffer slash inverter is important. Like sometimes we want a number to be inverted and sometimes we don't. The way we do subtraction is we'll invert a number and add it to the other number, and we'll, through a couple other things, we'll get a subtraction. So sometimes we want to invert those numbers, okay? Now watch this. Go ahead and stop. I'm going to give you a little thinking thing, all right? We can tell if it's unequal, like if the input and the output are not equal, right? But what if we wanted to see if it was equal? What could we do? Could we just put an inverter on the end of an XOR and see if the two things are equal? Right? Yeah. You'll see what I'm saying, right? If we put an inverter at the end of an XOR, it's going to show us if the two numbers on the two things are true or not, or equal, right? All right, so that doesn't seem that amazing with one bit. If they're both 0, it's on. If they're both 1, it's on. But what if we did that for a bunch of bits? Let's say for, y'all know how to count in binary from 0 to 7, right? 0, 0, 1, or 0, 0, 0, 0, 0, 1. I don't want to do that, man. Let's just go up to 4. So 0 through 3. All right. Let's say we got a combination lock and we got 3 switches. And the combination can be either 1, 0, 1, 2, or 3. And it's going to open. Okay. All right. So let's make a simple combination lock. All right. Let's take, we need an XOR for each bit that we're going to do. Okay. Now the XOR is going to tell us if those two bits are not correct. So we're going to put an inverter on the end of each one, because now each one will tell us if those bits were correct. Right? All right. If all 3 of those bits are correct, or we're just doing 2, aren't we? Yeah, we're doing 2 bits. We're doing 0 through 3. So let's delete these. If both of those bits are correct, we want the machine to let us in. So what will we do? We need something that will show us if both of them are correct. So we need an AND gate right there, right? So if both of those are correct, if this one and this one are correct, then let us in. All right. So over here, instead of doing a bunch of input switches, let's do an input dip switch. Okay, so scroll down and do a 4-bit input dip switch. And that'll give us 4 switches close together. Okay, so put one up top. Okay, and let's label that secret code. Okay. And then flip it around. Well, yeah, flip it around, but realize that well, it doesn't really matter. We're going to call this keypad. All right. So somebody's going to come up to our door and have to put in a combination. All right. Cool. All right, get some wire. And now this first bit over here, we're going to compare them with an XOR. And the XOR is going to tell us if they're different. Okay? If they're different, it's going to give us a 1, which then we're going to invert, which will give us a 0, and the door is not going to open, right? So all in all, what it's doing is it's comparing the two bits, one from my keypad and one from my secret keypad, right? And we're going to go up with the second bit and do the same thing. The second bit from both of them are going to the second XOR, okay? And then if both of those are true, or both of those are right, then the door is going to open. So let's go ahead and put an LED right there, okay? Now, when we run this, are y'all starting to see the power? We're using a really simple thing, but now we're getting some complicated things going on, right? We could have a big 8-digit one, or, you know, all kinds of stuff, right? Now, this way's a little cheesy in the fact that, like, I could keep putting numbers in until that light comes on, but couldn't we put a counter in there and say you only got 4 tries, and then put another button in line with that AND gate so that I'd change it and then I'd push the button and then it'd check it? And if I was wrong 5 times, then we would lock out. We'll get more complicated with it, but we don't have to right now. We're making a comparator. We're comparing 2 2-bit numbers. All right. So when we play this, it's on because both of them are 0. Let's say I went and changed my secret code, right? Now the only time this is going to be true is if they get the same secret code. If I try 3 right there, it's not going to be right. Is it not on? Or is y'all's brain starting to get bigger and like start to go, oh man, I can build anything now, right? Because those ANDs, ORs, and NOTs, we can build anything. Now we've got XORs in there, but you have to realize that those are just ANDs, ORs, and NOTs also, right? We abstracted them. So we don't have to think about the ANDs, ORs, and NOTs anymore because we've got a function that we like. We could abstract this, make a box and say, you know, put numbers in over here and numbers in over here, and we'll tell you if they're equal, right? And we do that. All right. So now we're comparing 2 different numbers, and we're going to be able to tell if they're equal or not. The only time that light comes on is if the secret code and the input pad are exactly the same. Y'all feeling what I'm cooking? Like, this is one of those reasons why digital changed what I wanted to do with my life. Like, it always bugged me, how did the TV work? How did the computer work? And it all comes down to this, right? Like, the stuff we see on our screen are pixels made out of red, blue, and green little dots of light, okay? And when we decide, you know, to turn those on in a certain order, it looks like, you know, me up there on that screen, okay? So we just made a comparator right here, right? Now, when you get into De Morgan's was the thing that really messed with me. And you're about to hit it next week. But De Morgan says that if I have something with all of my inputs as inverted, it's the same thing as the opposite thing with the output inverted. Okay? So I'm giving you a little give me when you get into De Morgan's, and it gives you a little chapter on the inversion of an OR, when it gives you that whole little paragraph of how De Morgan's works. At its heart is I could make the same circuit. I'm just going to show you that for a second, right? Inputted inputs of an AND gate is equal to inputted output of an OR gate, and vice versa. If I had an OR gate with inverted inputs, it's the same thing as an AND gate with an inverted output. It's confusing, but what that's saying, like, that's really powerful because right here I've got three components, right? Now, y'all saw how that worked. Don't put this in, but what I'm going to do is I'm going to prove it to you real quick. Okay. So I'm going to put an OR gate in there. Yeah, like all right, what it basically says is if you have inverted inputs, all inverted inputs is the same thing as the opposite gate with inverted outputs. All right, so, I just got rid of 2 knots and I put 1. So I just saved myself 1 component, didn't I? If this works the same way. Now, that's not that big of a change, but when we start simplifying circuits and you have 100 things that you could simplify down to 5, that gets pretty important, right? So let's watch this real quick. So they're both the same. I changed that. So even if you don't completely understand how that works, we're going to talk about how that works and we're going to build how that works. But in your heart that it works because it's working, right? Like I took an OR gate, put an inverter on it, and it operates exactly as an AND gate with all of its inputs ANDed. All right, cool. I just simplified it. We're not getting to simplification anymore, but I just thought of De Morgan's, and I know that that's going to be a roadblock for you whenever you read it in the book. But all it's saying is that if you got a lot of, like, let's say I had a 20 input AND gate, right? And all of those were inverted. I could turn that into an OR gate with 1 inverted output, and I just saved myself 20 knots. And it works the same way. Now, once y'all read De Morgan's, I'm going to go and we're going to do something in Deeds to prove that. I just proved it, but we'll go in and through truth tables and stuff like that, we'll prove it. All right. Yeah, when they're both the same. So.
My main question was it didn't look like it worked on the boards. I was wondering why I did wrong. It registers when they're both 0. And then when I input a 1, 0, and I try to do it on the other side, it didn't line up together. But when I pick it back up to both of them are 1, then it sparks up again.
Okay, make sure that second bit, this one right here, on each side is going to that XOR. Is it? That's the most common problem there. So I was able to make a circuit that was a little bit simpler, but it gets a lot simpler later. Like, I'm not going to show you, but like I could, like right now it'll just needlessly confuse you, but like I could give you a truth table that this, and this is true, and then you'd build a circuit with like 12 AND gates and be able to do it. And then I'd come back and be like, or you could choose 1 OR gate or 1 inverter, and okay, like, so, ANDs, ORs, and NOTs are, what we call, they're elemental. Like, you can't get any simpler than those, okay? Like, everything else we build are built on logic that are ANDs, ORs, and NOTs. So, really, the only real components that we have are those 3, okay? Like, when we build a comparator, or we just built a comparator, didn't we? We compared 2 numbers and saw if they were equal. When you build a multiplier, a multiplexer, a demultiplexer, all those things, they're built off of ANDs, ORs, and NOTs. Okay? Now, technically, now they're all built off of NAND gates, which is an AND gate with the inverter on the output. Like if you look at, specs for like solid state drives, they'll be like NAND technology and stuff, right? But a NAND gate is not an elemental, but a NAND gate can become anything. Like with a couple of NAND gates, you could become an AND gate, or you could become an OR gate, or you can become a NOT, right? And what it comes down to is, like, let's say I'm using an FPGA, which is a field programmable gate array, and you can make a GPU from that. You can do a bunch of stuff. If I don't know how many of something I need, like I might need 50 million AND gates, but like 4 ORs, and I'm making a silicon substrate, and I'm trying to get the most out of it, right? It's not good to like put like a million ORs, a million ANDs, and a million NOTs, because some people might need a whole lot more NOTs than they need ANDs. Well, a NAND gate, which is an AND gate inverted on the output, can become any of the other 3. So we can get really good at making a NAND gate, and then that person could rewire that NAND gate to be any of the 3. Okay? I'm going to prove that to you for a second. All right? Just one of them. This is not for this week, all right? Like, y'all pretty much got the lab done for this week. You'll turn this in. Like, if you're watching the video, you'll have to build this. But let's put a NAND gate in here. I'm gonna put a 2-input NAND gate. All right. I want to make an inverter. Okay. I'll show you mathematician wise why this works when y'all get done with the Boolean algebra aspect. Okay. But if I tie both of these inputs together, I just made that NAND gate into an inverter. Okay, cool. Now, 0, 1 is an inverter. Well, a NAND gate is an AND gate with the inverter on the front of it. So that AND gate with the 0 on it, like instead of putting that big triangle after stuff, we sometimes use just a 0. Like, so if we have a AND gate with 20 inputs and 4 of them are inverted, we might have 4 zeros on the input. If the output's inverted, we might have a circle on the output. But I just proved that I made a NAND gate into an inverter, right? Okay, well, what if I wanted to, what if I wanted an AND gate from a NAND gate? Well, I've already got an inverter here, and a NAND gate is an inversion of an AND gate, right? So I could take this off, and I could put another NAND gate in. And what I'm doing is I'm inverting the NAND gate because I just proved that was an inverter, right? And so with nothing but NAND gates, I made a AND gate. So y'all know how an AND gate should work. The only time that light should come on is if both of those are true, right? We've got an AND gate with using nothing but NAND gates. All right, with De Morgan's theorem, I said that like inverted inputs of one gate is equal to the opposite gate with the inverted output, right? So that De Morgan's helps us get from an AND to an OR. So what do I want for an OR gate? Well, no, I'm still going to use NANDs, right? But I want to convert that AND into an OR, right? All right, so what I'll do is I've got these inverters here, right? and I've got this NAND. All right, so now I've got both inputs of the NAND. Yeah, like by tying both inputs together. And we'll get specific about why that works, right? But if I invert the inputs, all the inputs of something, it becomes the opposite with the inverted output, right? Okay. So if this was an and right here, it would be a nor with the, or it'd be an or with the inverted output, right? But we've already got inverted output. So let's see what this gives us, okay? I wasn't planning on teaching y'all De Morgan's, which I'm not really teaching you De Morgan's. I'm giving you a little food for thought so that it's easier when you read De Morgan's, okay? All right, well, I'll be darned. Doesn't that operate just like an OR gate? Like if either one of those are true. So I just proved that with the NAND gate, which is ands, ors, and nots, right? I can make any other thing with just an AND. Now that makes it cheaper because I can make a substrate with nothing but NANDs and let the person decide that if they need 1,000,000 ORs, they wire it up to be an OR, right? And they don't waste as much. You know, if I did thirds, like a third of it was ANDs, a third of it was ORs, and a third of it was NOTs, you know, we might be wasting a bunch of, you know, stuff. You know, we might run out of one where we've got plenty of the others. Well, you know, I can focus on getting really good at making NAND gates and just give you 1,000,000 of them. And then you can make an and or not as you need it. And you're not wasting any of that space, right? All right, so we'll talk about how a NAND gate is an and or and a not right now, actually. Because all a NAND gate is an AND gate with an inverter. That's all a NAND gate is, right? But if we hard code it, if we make the substrate actually give us a NAND, right? We can make all the rest of it. Okay? So that's why they call a NAND gate a universal gate. Like we can make anything out of it. Okay? And that's what we do. Like NAND flash technology. You know, we get really good at making one thing and just make it over and over again. Interesting? A little bit. All right? Like this is right on the cusp of us being able to make actual useful things out of this. All right. So this was the first little one, right? Well, actually, you'll see the use of a switchable inverter later, but we're comparing two numbers. We can get going.